Everybody, this is a problem that's similar to SMO 2023. Now notice that what we're trying to evaluate is a floor function. And notice right off you can get a decent estimate by just noticing that this is approximately equal to the floor of 7 cubed. Okay, and the reason is the square root of 11 is slightly bigger than 3, right? Square root of 9 being 3, so the square root of 11 is slightly larger than 3. Right, and so we have this approximation right here already. 7 cubed is what, 343. So this would be somewhere around 343, and be somewhere, within shouting distance. Now let's talk about what we mean by the floor function. Let's use a concrete example here. Let's say that we want to do the floor of 7.8. Now this is very intuitive. You essentially just chop off the decimal portion of the Hindu Arabic number. And in this case, when you chop off the 8, you get 7. Now notice, again, you don't really, this is just a formal definition right here, but that's because 7.8 is bounded below by 7 and above by 8, right? So you have 7 less than or equal to 7.8 less than 8, right? 7 plus 1 is 8. Okay. So this is formally why the floor of 7.8 is equal to 7. That's also called the greatest integer function. Now let's get busy solving the problem because this is an irrational expression. Now, so it certainly makes sense to expand out 4 plus the square root of 11 quantity cubed. This is the familiar pattern from Pascal's triangle or the binomial expansion. There's the well-known 1 in front of this. 3, 3, and then another 1 right here, right? Well-known pattern when you cube a binomial. All right. Now the arithmetic is done for you right there. 196 plus 59 root 11. Now at this point, you don't really know quite how big square root of 11 is. You know it's bigger than 9 and quite a bit less than. You know it's bigger than 3 and quite a bit less than 4. But you don't know really what 59 times root 11 is without using a calculator. Okay. So what we're going to do is try this idea of bringing the 59 that we see right here back inside, okay? And we'll get a large number when we do that. Now this is a pretty tedious computation by hand, but this is correct. I've double checked it. All right. Now the next thing to do right here is find out what two perfect squares this radicand is between. 38, 291 is trapped between 195 squared and 196 squared, okay? Now, so that's tedious. I'm not going to joke to you about that. Now, if you square root both sides, you get 195 is strictly less than the radicand, or the square root of the object here, the square root of 38, 291. I hope you see this is kind of neat. It's computationally burdensome, but it's really our only path to Rome if we're not using a calculator. So we have 196 here. Okay, you see our radicand fits right in with this definition. That means the floor has to be, the floor of this object has to be 195. Okay, in other words, this is a little sloppy writing it like this, but the floor of just this piece alone is 195 based on our definition of what a floor function is. Okay, and so what we can do, we can finish this thing off rather quickly by writing this as 195 plus 96, or excuse me, 196 plus 195. So you have 195, okay, plus 196. Okay, and what is that? 391, 380 plus 11 is 391. So the answer to this one is 391. Now, again, I did double check with a calculator, but all the work is doable by hand. So that is the solution. Hope you guys liked it. There is another way to do this using alternating series, which I might do in the following video.